Okay, in this video, we're going to talk about sensible heat ratio. The sensible heat ratio equals sensible heat divided by the total heat. In HVAC design and equipment selection, it's vital to understand what the space sensible heat ratio is during full load and what the potential SHR or sensible heat ratio is at part load. Knowing the sensible heat ratio at full and part load will allow you to design and properly select the equipment that will control temperature and humidity over all load conditions. Okay, so let's get to it. Let's calculate an SHR, sensible heat ratio, and we'll plot that on the psychrometric chart, and we'll have a look as to how changes in the SHR could affect your resultant temperature and humidity levels. So let's take this general office space as an example, and let's say you took out your favorite load program and calculated the load on this space, taking into account all the people, the total sensible, and the total latent load that would happen in this space during full load and part load conditions. Okay, you've run your building load, your sensible heat comes out at 80,000 BTUs per hour, your latent heat comes out at 20,000 BTUs per hour, so your total heat load on this space is 100,000 BTUs per hour. And like we said before, the sensible heat ratio is the sensible heat divided by the total heat. So we'll go ahead and plug these values in there. Again, 80,000 BTUs per hour was your sensible heat. The total heat load is 100,000 BTUs per hour. So the SHR for this space is 0.80. We typically just call that a 0.8 SHR. And 0.8 is a common SHR for typical office spaces, but never, ever assume your sensible heat ratio always perform a heat load calculation. Okay, so let's look at plotting the sensible heat ratio on a psychrometric chart. If you have a chart printed out and a straight edge, you can pause this video and play along, or just sit back and watch, and I'll show you how to do it. Okay, the first thing you're going to want to do is find something called the index point. Now, some charts are a little different. The way this chart works is we're going to draw the SHR by finding the index point and lining it up with the sensible heat ratio numbers, which are on the right. And here is the index point on this particular chart. And there's a better shot of that there. I blew up the graphic for you. Okay, now we've moved over to the right-hand side of the chart, and you can see right here the sensible heat ratio, which is QS over QT. And I'll blow this up here for you. So sensible heat ratio, QS, Q sensible, or your sensible heat load in BTUs per hour, over QT, Q total, which is your total heat load in BTUs per hour. And you see these numbers right here, starting at 1.0, 0.95, 0.9, 0.85, 0.8. Those are the sensible heat ratios. So we're at 0.8, which is about right. I can't reach it. Right there. Okay, right there. Okay, so easier to draw an arrow. So it's right. Where am I? Right there. Okay, right there is the 0.8 SHR. So what we're going to do is we're going to take the SHR on the right, or is that my left? And we're going to line it up with the index point over here. Okay? Okay, now get ready. We're going to do that with the ruler. Let's see if I got this right. Boom. Okay, we nailed it. So 0.8 SHR, we're going from here on the SHR points on the right, and we're lining that up with index point here. And we'll go ahead and digitally fill that in with a line here. If I can get my clicker right. Okay, so now we have drawn a 0.8 SHR. Now here's what's important to note about this line here. What's important is the ratio or the slope or the slant, not necessarily the location. So you can move this line anywhere, up or down the chart, and as long as you're keeping the slope the same, you're always representing a 0.8 SHR, which is the ratio of sensible heat to total heat of the space. Okay, so here's why it's extremely important to understand SHR and to know your SHR at full load and part load, okay? So this is a full load SHR of 0.8, and let's say the room design is 72 degrees dry bulb and 50% relative humidity, which is located right here. By the way, if you need a tutorial on how to read the psychrometric chart, check out our YouTube channel, HVAC On Air. All right, enough of the commercial interruptions here. So now we've plotted our room design of 72 degrees dry bulb and 50% relative humidity. Okay, So let's say you have this system, you're providing X quantity of CFM to the space, and I like to think of the air as a sponge. As it enters the space, it's going to absorb sensible heat and latent heat, and you want the air to absorb the sensible latent heat in the correct ratio such that you end up in your design intent, which in this case is 72 degrees and 50% relative humidity. So you see I've got some numbers there. If you provide air to the space anywhere along this line at 0.1, 0.2, 0.3, any of those conditions, at the right quantity of CFM, you will end up at your design intent. Now, typically, we're going to be somewhere around the number 1 mark because we're leaving the coil in a saturated state. So typically, we'll be right here, which is in the 50-ish degree range, leaving the coil. And if you put it in there in the correct quantity of CFM, it's going to absorb heat and humidity along the sensible heat ratio such that we end up at our design intent. So again, we want the sensible and latent heat to be absorbed in the correct ratio so that we end up in a comfortable space, a cool and dry space. If we take out too much sensible heat and not enough latent, we'll end up over here on the psychrometric chart, which results in a cooler and damper space condition. If we take out too much latent heat and not enough sensible, we're going to be over here in the psych chart, which is a warmer and drier space. Okay, so what happens at part load? And this is where most designs fail. It's very easy to control temperature and humidity at full load. It is at part load where most systems will struggle to control temperature and humidity if they're not designed and selected properly. Okay, so here's a typical scenario. You have your entering coil conditions here, going through the cooling coil. As it reaches saturation point, you start to remove temperature and humidity. Since we've calculated the SHR and have selected and designed the system properly in the correct CFM, this air is going to enter the space and absorb heat and humidity to end up in our resultant design point. So what happens when our sensible heat ratio changes? So you can see here I've crossed out the 80,000 BTUs, which was the full load sensible heat on this space. Let's say it's a cloudy day, there's less people in the space. A cool and rainy day is a classic part load situation that can cause high humidity levels in the space. Let's say our new sensible heat is 47,000 BTUs per hour. So if you look at this equation, and for sakes of this example, we're going to assume we have a constant volume system at 3,200 CFM. What could change here to make this equation balance? It's very obvious your supplier temperature has to change. So here's a graphical representation of the full load condition we just talked about. You could see the supply air is 32,000 CFM at 49 degrees, dry bulb. At full load conditions, what happens at part load if you still blow 49 degree air into your space? In this particular example, it's going to overcool the space. So you have to throttle back the supplier temperature. You could do that by cycling the unit. Let's assume this is a fan coil with a modulating valve, and we're throttling. All right, one more time. I think I'm going to get this right. And we're throttling. Oh my gosh, I couldn't get that out. The chill water valve, and our supplier temperature is now 58.4 degrees because we've run it through this equation again. We solve higher temperature. So what's our new part load SHR? If you see below here, it's 47,000, which is our new sensible heat for the space. And our new total is 67,000 BTUs per hour. I've taken some assumptions here that the latent hasn't changed a whole lot. So just for sakes of this example, to make it easy, this is our new sensible heat ratio. So it went from 0.8 to 0.7. Okay, so we're back here at the chart, and the new supply air is 58.4 degrees because we're throttling back our chill water valve because we don't need as much cooling. So let's plot that on the psychrometric chart. So D prime is our new coil leaving air temperature. I'll blow that up here for you, which you can see is about 58 degrees, a little more. Now we're going to draw our new sensible heat ratio through the index point, okay, which is 0.7. So the air at D prime, when it goes into the space, it's going to absorb heat and humidity in the ratio shown in the 0.7 SHR. If we move the SHR up, we can see where we're going to end up on the psychrometric chart in that space. And we'll call that A. That should say A prime. All right, so here's the headline here. Here's the story, the main thing you need to get from this video, which, by the way, thanks for watching. If you're still watching it and hanging in there, we appreciate you. Here's the main thing to get. Look at the relative humidity at point A. It's 50%, right? 72 degrees, 50%. What is the relative humidity at the red A, which should say A prime, but the red A, what is the relative humidity there? It's 70%. Same temperature, higher relative humidity. That means it has a total humidity level that's higher in terms of grains. That's another video. But the humidity level is higher at A prime than it is at A. And therein lies one of the struggles of constant volume equipment with modulating chill water valves to control temperature and humidity over all load conditions. If this was a common office space, and this happened a few times a year, probably not that big of a deal. If this was a critical application and we needed to maintain specific temperature and humidity over all load conditions, this could be a major issue. So the point here is to make sure you understand sensible heat ratio at full load conditions, perform proper load calculations to understand the sensible heat ratio at part load conditions, and then make sure you select the equipment that has the features and controls and sequences of operation such that you control temperature and humidity over all load conditions.